All right, so welcome to class, everybody. I want to go back and review a little bit. Last time we derived the heat equation. This is also called the heat conduction equation or the heat diffusion equation. I typically just call it the heat equation. So if you remember, this is an equation. It's based on a differential energy balance. So just to help our brains, we sort of imagine a big solid mass, and we divide it up into little cubes. And then we take one of those cubes and do an energy balance on it. So because this cube is completely embedded within this bigger mass, the only way that heat can get in or out of it is by which mode? By conduction. So it's just on conduction, except at the boundaries of our mass, there will be other things happening like convection or radiation. So, but we go and do this energy balance on one cube and then assume that that same math can apply everywhere throughout. The temperature might change, but the form of the energy balance is the same. So then we go through, we did this energy balance on the cube. This is all, we had our accumulation, and then we had in and out in the X, Y, and Z directions. We also made this general and added generation in there, which may not always be the case. And we ended up shrinking our cube down to 0 by taking the limit as every side of our cube goes to 0. So that makes our cube infinitesimally small, which makes our equation continuous. So by solving this partial differential equation, we can get temperature as a function of time and also X, Y, and Z. And ideally, you would have a really nice, beautiful looking equation. And if you wanted to know what the temperature was at any point inside that big mass, you could just plug it into your equation. Turns out that it's never that easy. If you've had PDEs, then you'll know that solving these equations can be extremely difficult. So what we'll end up doing is coming up with ways to simplify the heat equation and solve it for specific cases so that we can get a solution that makes sense to us. Or we will take a numerical approach and solve the equation numerically, which is actually an extremely powerful tool, and we'll get into that a little bit later. So we end up with this heat equation. This is the form only when you have constant thermal conductivity, and this form above is when you may not necessarily have constant thermal conductivity, where thermal conductivity varies as a function of temperature or as a function of distance or direction. Okay, so we got the heat equation, and then we asked some questions. We tried to demonstrate how for a certain system, because of symmetry, you can take out certain terms, or if the system is at steady state, you no longer have your accumulation term. So we did that for a couple of examples, and we ended here, I believe. So on the boundaries of our system, so we'll get this heat equation. It's a differential equation, so we're going to go through that process of doing separation and integration and solving this equation. So when you do that, you end up with constants of integration, which are sort of meaningless until you apply the boundary conditions. So at some point when we solve this equation, we'll apply boundary conditions, and that'll take us from this generic form of the equation that has arbitrary constants in it to terms that actually make physical sense to us. Any questions so far? I'm reviewing this in more detail because it is really important. The heat equation is central to conduction, and it's a really powerful equation. So I want us to get familiar with it, and more specifically, I really want to get the whole class in this mode of knowing how to define a control volume and to apply an energy balance and to solve that energy balance to give you a lot of useful information. So I want to really encourage that systematic way of thinking because that is extremely powerful, not just for heat transfer, but for a lot of other classes. The similar idea in fluids and in mass transfer, where it's all about taking a balance of your system, whether that's energy, like in this class, or whether that's momentum, like you'll get in fluids, or whether that is mass or species conservation, like you'll get in mass transfer. The same ideas apply. So if you can get yourself into that mode of thinking, you'll be able to solve a wide range of problems and just generally understand some of these concepts better. Okay, so the heat equation, I gave you that simplified form where we were able to pull out K when K is constant, K being the thermal conductivity of our solid or stationary fluid. So K may actually vary depending on, it'll certainly vary depending on the material. It may also be a function of temperature or which direction you're going in. So for certain materials that might have like a certain crystal structure, maybe the atoms or molecules are closer together in the x direction versus the y direction, so maybe the conductivity will be different. We won't deal with this very much, but this is just sort of posing the idea that thermal conductivity may vary with either spatial dimension, as in that picture above, or with temperature. So as the temperature changes, your thermal conductivity might also change. And just as a hint, for your next homework, you're going to have a problem where the thermal conductivity will be a function of temperature. It just makes, I really want you guys to just go through this process of integrating the heat equation. So whereas the book covers a lot of like simple cases, and then they give you all the temperature profile equations that are the heat equation solved basically. But you'll have a homework problem, I think it'll be number 1 on your next homework, where you have to do this integration assuming that thermal conductivity varies with temperature. But in general, usually it's a pretty good assumption that thermal conductivity is constant with temperature. Okay, so there are certainly micro and nanoscale effects. So the thermal conductivity is actually a function of the mean free path between atoms or molecules in a medium. So there is some theory that goes behind all this on the molecular scale. We're not going to get into that too much. Yeah, that's about it. So that wraps up chapter 2. And I meant to finish chapter 2 last time, but wanted to go through and just cover those other topics. Okay, so now chapter 2 is sort of introduction to conduction. Chapter 3 gets a little bit more into some of the intricacies of conduction, and specifically we're going to take one specific case of conduction and solve problems where these certain assumptions apply for our solid. So this is called one-dimensional steady-state conduction. Give me just a minute. So one-dimensional steady-state conduction just means that energy is only going to be flowing in one dimension, so that might be the x or the y direction for a Cartesian coordinate system, or it could be the radial direction for a cylindrical system. We had those interactive questions last time where we thought about how many dimensions we needed to model a specific system, and it was, I think for some of us it was kind of challenging to take a three-dimensional object and try to transform that into a specific coordinate system where you might reduce the problem down to one dimension. So we'll work on that as we go. So one-dimensional steady-state conduction is generally going to be energy traveling through a plane wall. So we've talked about this plane wall example. We'll talk about it more. That's for the Cartesian case. For the cylindrical case, it's going to be energy traveling through a cylindrical wall. So think about like a pipe or a tube, and how does energy get from the inside of the pipe through the pipe to the outside. So that is a one-dimensional problem. Even though the pipe has curvature to it, you could describe that problem with just the radius outward from the pipe. That would be assuming that there's no temperature variation axially or down the length of the pipe. And then the final case would be a spherical shell, which is same idea. You just have a sphere. You might have a spherical chemical reactor where there's a reaction happening. So this one-dimensional steady-state conduction would apply when your system is at steady state and you have heat going from the inner side, the inner shell of the sphere to the outer shell of the sphere. But again, there are many cases where that could be a one-dimensional problem. And even though the spherical heat equation looks kind of nasty, we can greatly simplify that. Okay, so we are going to, have you guys heard me use the term shell balance before? Okay, so a shell balance is basically what we did when we derived the heat equation. We took a big solid and we broke it up into smaller chunks, at least mentally, and we did an energy balance on one of those smaller chunks. Then we applied that energy balance broadly to the whole system, to the whole solid, and had this really nice equation. So a shell balance is basically the idea of taking a system and breaking it up into smaller pieces and putting an energy balance to those smaller pieces so that collectively all of those pieces would give you critical information like temperature throughout the whole thing. So for a plane wall, if we had, and there will be a point to this, it may not be clear until about 5 slides from now. Let's say we have a room on the left of my screen and a room on the right. And between them we have just this dividing wall. So if this room, let's call this T1, let's say this is 30 degrees C. And the other room is, let's call that 15 degrees C. All right, so how, just given your intuition and the discussion we've had in class about temperature driving forces, how is heat flowing in this system? Which direction, I guess? Okay, I'm seeing some hands pointing, so it's flowing from left to right. So because the temperature, it's going away from that hotter room, which has more energy, and it's going propagating through the wall into that other room. So if we just want to think about, we don't want to think about the convection that's happening on each side yet. We just want to think about conduction through the wall. But we want to come up with an equation that describes the temperature profile going through the wall. Let me make this a little bit simpler. So let's say that these temperatures actually describe the actual wall surface temperature rather than the room temperature. Okay, so what we would do to do a shell balance is we would take, so assuming that this is a big wall and that the air is all well mixed on each side, it would be a very reasonable assumption that temperature doesn't vary in this direction, let's call that the z direction, and it also doesn't vary in the y direction, which would be like coming in and out of the screen here. Okay, so we have no temperature variation in the z direction and no temperature variation in the y direction. However, would we expect temperature variation in the x direction, which would be just going through the wall? Yeah, so we would expect temperature to vary because it's got a surface temperature on the left that's 30 degrees and a surface temperature on the right that's 15 degrees. So naturally, we're going to see some kind of gradient going from left to right, which means heat transfer will be occurring in the x direction. Whereas in the z direction, there's no driving force for heat transfer. We can neglect what's happening in that direction. Same for the y direction. Okay, so that makes this a one-dimensional problem, which means we can take our shell, we can define a control volume that's just a thin slice out of the middle of this wall. So we just have a nice thin slice going through the wall. Let's make the assumption that there's no generation. I don't know why a wall would be generating heat, so it's not in this case. So no generation, and let's also assume that you have maybe a heater in this left room and maybe you have the AC on in the right room, and you set the thermostats and just wait for 10 hours until this whole system reaches a steady state. So a steady state, that means we have no accumulation in our system. So our energy balance, so we're just going to do an energy balance on this thin slice of the wall, which I'm going to call a shell. So if we did our energy balance, we have accumulation is 0. We have an in term. We also have an out term. Let's call this thickness of this little slice delta x. So this going from left to right, we'd be x distance from the left edge of the wall here, and then here would be x plus delta x. Okay, and then, okay, steady state. So if we just set the thermostats in each of those rooms, the room on the left to 30 and the room on the right to 15, and just waited, things would eventually reach a steady temperature? So that's a good question, actually. So I want to ask another question. Would that be thermal equilibrium? It would not be thermal equilibrium. So thermal equilibrium would mean that everything is at a uniform temperature, so you have no flow of heat. So steady state, it's an important mental distinction to make, that steady state means something different than equilibrium. Sometimes they're the same, like if we set both rooms to 30 degrees and then waited, they would reach a steady state where everything, including the wall, is just at 30 degrees. But you can have a steady state and still have heat flowing. Does that make sense? So thermal equilibrium would be where everything reaches the same temperature and there's no more flow of heat. Steady state, you can still have heat flowing, it's just flowing at a constant rate. So we're still going to have a constant flow of heat from the left to right at steady state. And there's still going to be this temperature gradient from the left room to the right room and through the wall itself. All right, so we go back to our energy balance. So we have generation is 0, mainly because we're told that. Generation is more the exception than the rule. Okay, so into this little slice, this imaginary slice that we've taken from the middle of the wall. Again, it's not exposed to either edge. It's embedded right in the middle of the wall. How is energy getting in? Which mode of heat transfer? All right, so energy is getting in by conduction, and it's getting out by conduction as well. So we can do, our in term is going to follow Fourier's law. Minus k dt dx, and then we would also need some sort of area, some sort of normal area to the flow of heat transfer. So that would be, we could just take a basis of 1 meter in the y direction and in the z direction, or we could just have delta y times delta z, and we'll just hope that those go away later. Okay, then we also have our out term. And this, I do want to point out, this is going to be evaluated at x. So the out term, and again, this just, don't let that negative fool you. Energy flows by Fourier's law, the flux is equal to minus k dt dx. So just remember that, and don't, just because this is negative doesn't mean it still can't be an in term. And your temperature derivative may flip, and that may become positive. Totally within the realm of possibility. So for now, let's just assume that, well, let's just apply Fourier's law without thinking too much about this. Okay, so out is going to be the same, except that we're going to evaluate this temperature gradient at x plus delta x. And we would still have the same area. Okay. So the next step would be to put this into equation form. So pay attention here. We have the energy balance equation is accumulation equals in minus out plus generation. So we're going to have, this is going to stay positive, the in term. The out term is going to flip in sign because we subtract the energy that's coming out. So let's put that into equation form. So we're going to have 0 accumulation is equal to in and then we're going to have minus out, but which would be minus negative k dt dx evaluated x plus delta x. Okay, so one thing that we're missing is our delta y times delta z term. So what can we do with that term at this point? We can just get rid of it, or speaking more from a more rigorous mathematical approach, we could divide both sides of our equation by delta y times delta z. So we just divide both sides of the equation by delta y times delta z, and we end up with just that equation. So that is also equal to, so we would have k times dt dx at x plus delta x minus dt dx at x that whole term equals 0. And there's actually another little trick we need to do here, which I neglected. Let's also divide both sides of this equation by delta x. I should have done that earlier. Okay, so what is this guy looking like now? That's looking like the definition of derivative, except it's the derivative of a derivative. So if we take the limit now as delta x goes to 0, we end up with an equation that looks like this. 0 is equal to d by dx. Our k is going to be embedded within this other derivative times dt dx. Okay, so this equation is based on an energy balance from doing this shell balance through a plane wall that's at steady state and that has no generation. So this is actually a fairly simple equation. It's still a second order differential equation, but we've removed a lot of the ugliness of the heat equation. So that's the shell balance approach. That approach is extremely valuable. So we'll get to this later on in the semester, but by doing this approach, instead of getting to the point where we shrink down our delta x down to 0, we could actually just keep that as a finite number. Let's say we want to divide our wall into 10 different sections, then we could keep this in discrete form, and we would have 10 equations and 10 unknowns, and you could just plug that into Excel or MATLAB or Python, and you could just solve that system of 10 equations and 10 unknowns. You would have made this discrete approximation of the heat equation, but then using software, you could actually get a pretty good approximation of what the temperature profile looks like. So that approach doesn't get all that much more complicated when you're dealing with 2 dimensions or 3 dimensions. It just becomes coding and organizational skills that help you to solve that problem. So while trying to integrate that second order PDE that varies with time and with 3 dimensions, that gets extremely ugly and extremely complicated to do that analytically. To do that numerically becomes really easy. So we'll try to make that connection here in a few weeks where you guys will learn to solve some of these problems numerically by just stopping at this shell balance, assuming that your shell stays a finite size, and then solving the problem numerically. We'll make that connection later, I promise you. Okay, so we've got to this point. So basically, we can now solve this equation. We would do the integration, and we'll step through problems where we do that, probably today. So we would solve this for temperature as a function of x. So by solving this equation, we will then have another equation that tells us if I plug in x, I'll know what the temperature is at any point in the wall. Okay, so remember that functional form of this equation. Remember how that guy looks. It's fairly simple. So this is actually a form of the heat equation. We just derived the heat equation again, only this time for a very specific case, which would be a plane wall system. So we neglect temperature variation in x and y direction. Steady state, so we neglect our accumulation term, and no generation, so we neglect the generation term. There's another way of doing this, which would be how you'll want to solve a lot of your homework problems. So instead of doing that, we could also look at the full form of the heat equation, which looks like this. So we have rho Cp dt dt equal to the partial derivative with respect to x times k dt dx. I should have had this like printed and ready to go, but all right, so this is the heat equation. All right, so for that same kind of a system, our assumptions were steady state, plane wall, and no generation. Okay, so just from these assumptions, we could start here with this general form of the equation, and we can just start crossing off terms. So help me out here. The steady state term, what is that? The steady state assumption, what term does that allow us to get rid of? Okay, so no accumulation because of steady state, great. How about this assumption of a plane wall? Okay, so because it's a plane wall, we get rid of y and z. And then the easiest one is last. So we end up with 0 is equal to d by dx times k times dt dx, which, if we look at this, this is no longer a partial differential equation because there's no variation of temperature with anything besides x. So that just becomes a second order ordinary differential equation. All right, and does that look familiar? So that's the same. We got to that same point by doing the shell balance. The shell balance we did is just a simpler version of the heat equation derivation that we did on Monday. So we get to that same point, so that you can just start from here from the heat equation. And if K, our thermal conductivity, is constant, then we can just pull this out. We don't need to take the derivative of it because it's constant. So then we would get 0 is equal to K times the second derivative of temperature with respect to x. We can actually do another little trick here, which would be to divide both sides by K, assuming that we have a non-zero thermal conductivity. That's a fine mathematical operation. So if we divided by K there, then we would just get 0 is equal to the second derivative of our system. Okay, so who has intuition that tells them what the shape of our temperature profile is going to be based on that equation? Someone said it. Yeah, just linear. So the second derivative is constant, meaning that there's no curvature to our line. So for these assumptions, steady state with a plane wall and no generation and constant thermal conductivity, I'll add that, we would just expect our temperature profile to be linear. So the second derivative tells us there's no curvature to the line, but it's still going to have a first derivative that may be non-zero, so there will still be a slope, but it wouldn't have curvature. Okay, so I just wanted to show you how these two methods converge, how doing the shell balance, this differential energy balance, or just starting from the heat equation gets you to the same point, depending on your assumptions, because the heat equation is based on a differential energy balance. We just did a simplified version of that by applying our assumptions first. Any questions so far? Okay, and this would be something to write down. The homework problem, it's going to be your first homework problem. It's basically going to be recreating these two methods, but when you don't have constant thermal conductivity. And the idea here is to help get you in the mode of solving problems like this, doing the integration, comparing this shell balance approach to this heat equation approach. So the heat equation approach is sort of a shortcut to just getting where you want to be. Okay, so once we have this equation, this 0 equals the second derivative of our temperature with respect to x. So now we can just solve it for temperature. So we've got 0 equals the second derivative of our temperature with respect to x. Okay, so what do we do first? Okay, so we would, let's do a separation. And I'm going through this very slowly and methodically. These are like my favorite kind of exam problems because I want you guys to really develop a nice intuition for doing the integrations and coming up with these equations. That is sort of critical to understanding conduction. Okay, so we would separate. So let's just separate one of our dx terms. We would get something like 0 times dx is equal to the derivative with respect to x of dt dx. So we just sort of, wait, sorry. We don't have that. Okay. So we would do this integration. So on this side, what are we going to get? We're just going to get a constant of integration. So when we integrate, we just get this constant. And that is going to just equal dt dx. Okay, so we picked up one constant of integration. What do we do now? Okay, great. So we separated, then we integrated. Then we're going to do that again. So we would get c1 times dx is equal to dt. So we'll integrate again. And here we would end up with what? You guys are probably fresher in calculus than I am.
C1 times x equals C2.
All right, so we get our concentration, our constant of integration on the left-hand side, and that just equals t. Okay, so this is our temperature profile. So temperature is equal to some constant times some other constant multiplied by x. This is the basic equation. This is like y equals mx plus b. So that tells us a lot. We know that our temperature profile is going to be a line with some intercept and some slope. But we still don't know exactly what that slope is. Or we don't know what our intercept is. And we can find that out from our boundary conditions. So boundary conditions are what we'll use when we're dealing with spatial changes. Initial conditions are what we'll use when we're dealing with changes in time. But that's a great point, Peter. Thank you. Okay, so if you remember, we were sort of given our boundary conditions at the beginning. And this is why I made them these surface temperatures. So we have T1 on the left is equal to 30 degrees. T2 on the right is equal to 15 degrees. And we're going to expect our solution is just a straight line between those two. But let's go through and apply them. Okay, so we have our equation. Our temperature, which is going to be a function of x, is equal to C2 plus C1 times x. So at x equals 0, which would be the far left side of our wall, we have our temperature is just equal to T1. We could plug in 30 degrees. Let's keep it in variable form just to make our lives a little bit easier. Okay, so what do we do with this? Okay, so we can just plug it in right now. So we would plug in this T1 here. So T1 is equal to C2 plus C1 multiplied by 0. Great. So T1 is just, sorry, C2, our second constant of integration, is just T1, which would be that 30 degrees C. Okay, so then we still have, we can plug this back in now that we know what C2 is. So we would just have our temperature as a function of x is equal to T1 plus C1 times x. Okay, so we still don't know what C1 is. How do we get C1? Yeah, let's just assume the wall is L units thick. Let me just go back. I should have specified that. Okay, so our wall is L. That's our thickness of our wall. Okay, so how do we get this other constant of integration? So we still have one more boundary condition. So this is at x equals L, then we have our temperature is equal to T2. So we would plug those back into this same equation. So we'll plug in our x equals L there, and we'll plug in our temperature is equal to T2. So we would end up with T2 is equal to T1 plus C1 multiplied by L. Okay, so that tells us that C1 is equal to T2 minus T1 over L. Great. Okay, so now we know both of our constants of integration. Did I write C2 down explicitly? Yeah, okay. So C2 is just equal to T1. So now we just take those constants and plug them back up into this general form of the equation, and we get temperature as a function of x is equal to C2, so it's equal to T1 plus T2 minus T1 divided by L multiplied by x. So now we have an equation that tells us what our temperature is going to be anywhere throughout that wall. So this is about as simple as it gets with this temperature being linear. So the real thing to remember here is how we got to this point. We integrated the heat equation for this specific set of circumstances. With those certain assumptions that we made, we simplified the heat equation. We integrated it, we applied our boundary conditions, and after going through that whole process of solving the heat equation and applying boundary conditions, we end up with our temperature profile. We know what temperature is going to be as a function of x. The interesting thing to note here is that this actually doesn't depend on the thermal conductivity. That fell out of our equation. So in this specific case, thermal conductivity doesn't even play a role. However, when we apply Fourier's law, thermal conductivity will play a role again. Okay, so this is basically how you do a conduction analysis. You would specify the appropriate form of the heat equation. So we made the heat equation really, really simple. It was just became a second order differential equation where we cared about the second derivative of temperature with respect to x. We didn't have the generation term in there. Just having that simple, even if it were constant generation, that simple term makes things a little bit more complicated. So then we solved for the temperature distribution. So another thing that we're going to do is if we wanted to know the flux going through the wall, then we would apply Fourier's law again. But now we have a temperature profile equation that we could just differentiate it. We'd be going backwards a little bit. We'd differentiate the temperature profile equation, multiply that by minus k, and that would give us the flux going through the wall. So these are basically the simplest cases are one-dimensional steady state conduction with no thermal energy generation. And if we can add in that thermal conductivity is constant, then that makes it even simpler. So common geometries, we're going to have the plane wall that we just solved. We're going to have the tube wall or cylindrical wall where you'd have heat conducting outward radially from the center of a cylinder, or this spherical shell, which is heat conducting outward from the center of a sphere. Any questions so far? Is anyone totally lost? Just scratching your head about what's going on? Okay, cool, you guys are geniuses. All right, so for a plane wall, when we've made, and again, keep in mind this is only when we've made those assumptions, and I probably don't need to repeat them again. We have these implications. Our heat flux is independent of x, which is just to say that our heat flux is constant going from left to right through the wall, because what drives heat transfer for conduction, what's the driving force is the temperature gradient. So if we know that it's a straight line, we know that our temperature gradient is going to be constant, so that makes heat flux constant. Our heat rate is also independent of x because as you go through the wall, the cross-sectional area of a plane wall doesn't change as you go through. So the heat flux stays constant and the rate of heat also stay constant. So we applied these boundary conditions. I called them T1 and T2, but the book calls them TS1 and TS2. It doesn't really matter. So we got there by simplifying the heat equation and getting it down to that reduced form. And we ended up with a temperature distribution when you have constant thermal conductivity that looks like this. So if you had a material where the thermal conductivity was not constant, you would just make k, instead of we just divided through by k, we wouldn't be able to do that. You'd keep k in there, you'd plug in the functional form of k, and then you would just do the integration with that functional form of k. I'm giving you some strong hints on your first homework problem for the next time. It's that same basic approach, but one little twist to see if you guys can go through this whole process on your own. Okay, so all right, so if we took our temperature profile that we just solved for, T2 minus T1 over L plus T1, and we applied Fourier's law. So who remembers off the top of their head Fourier's law, or even a verbal description would be fine as well?
Flux equals negative constant times dt over dx.
Great. Thanks, Peter. Okay, so we could just, oh, and I screwed this up because I didn't put an x in here. Okay, so our flux would be, we just take the derivative of our equation with respect to x to get our flux. So what's the derivative of our temperature with respect to x? Yeah, so that is T2 minus T1 Okay, that's a constant, right? So our flux would just be taking this guy and multiplying it by x. So our flux in the x direction would just be equal to minus k times this delta t over L. So again, this only applies to a plane wall with those specific assumptions. It wouldn't apply if there was some even slight change to those assumptions. This equation wouldn't necessarily apply, but in this case it does. Okay, so one of the implications of this is that you can actually, so this method that we've been working at, it got pretty simple, I would say. And we go through this systematic way of applying the heat equation, integrating it, getting an equation that gives us the temperature. And this problem isn't particularly interesting because our temperature is just a straight line. However, sometimes when you solve this equation, you can get a whole ton of information about how the temperature profile is changing. That's usually the best approach there would be to use software to do this. But you could actually apply the heat equation to a solid in 3 dimensions and integrate it over time, and you can actually see 3 dimensions of temperature changing. That'd be hard to see. Let's say 2 dimensions of temperature changing over time, and that would basically be enough information to make a video about it, all from one single equation. So there's just a ton of information embedded within the heat equation, and it's just a matter of finding the right methodology to solve that equation to give you the information that you want. So with that said, there are some nice little shortcuts that we can take out of the heat equation. So one of those shortcuts is going to be something called this thermal resistance method, which, okay, let's just go for that now. So remember, we had our room. Actually, I'm going to go back to this slide. Okay, so let's look at this, kind of the same setup that I just described to you earlier. So we have heat transfer going from this left room to the right room. We alluded to this early on in the semester, but you could actually have heat that has to propagate through multiple modes of heat transfer before it gets to the left room, from the left room to the right room. So we talked about conduction, but really, if we want heat to flow from the air in that room on the left to the air in that room on the right, it has to convect from the room on the left to the left wall. Then it's got to conduct through the wall, and then it has to convect from the right surface of the wall into the room. So there would be 3 what are called thermal resistances between the room on the left and the room on the right. So that gets more complicated than just applying the heat equation. So if we wanted to quantify the amount of heat flowing all the way from here to all the way over here, first we're going to have to convect, then we'll have to conduct, and then we're going to have to convect again. So we need to factor in all those different things happening into one single equation. If we, let's say we don't know the surface temperatures, we only know the air temperatures, then we'd have to consider all three of those modes. So the approach that we're going to take is called thermal resistance method. So you've taken a circuits class, right? And you guys applied Kirchhoff's laws for where you add up the resistances that current has to flow through. This is the same exact concept, and the math is pretty much the same, but we're going to do this for flow of heat. We'll keep our circuits relatively simple for this, but we'll construct what's called a thermal circuit, where we'll consider this convection, the convection that has to happen from the left room to the wall. That'll be a resistance to heat transfer. Heat still has to get from that air to the surface of the wall somehow, so it has to overcome this resistance. Then it's got to get through the wall itself, which is going to be a conductive thermal resistance. So at the end of the day, when we're dealing with thermal resistances in series, and when we have heat going through different media, this is what our thermal circuit will look like, where this represents the temperature in room 2. This represents the temperature at the surface of the wall. This represents the other surface. And so at the end of the day, we want to be able to calculate how fast heat is moving through all three of these thermal resistances. That's still going to be a temperature driving force, but we're going to come up with this term, this R total term, where R total is the total thermal resistance. So I'm kind of explaining this in a roundabout way. Resistance. Okay. I'm a heat transfer professor, not a great speller. So our next step, which we might do on Friday, is going to be trying to get some better understanding of how do we develop this total thermal resistance. And actually, so for a plane wall, we just used Fourier's law. So this is the heat flux through a plane wall with those assumptions that we have talked about repeatedly. If we wanted to get our total rate of heat, that would just be minus K times delta T over L times the area of our wall. So to put this guy into that form, where Q is equal to delta T over this total thermal resistance, you can see that to make these equations equal, that our thermal resistance is going to have these terms. So our R total, the total thermal resistance for heat flow through a plane wall is going to be L divided by K times A. So this is a shortcut. I'll get my thoughts together a little bit better and go over this again on Friday. But this total thermal resistance for heat flow through a plane wall is just L over K times A. So just to build some intuition there, if L gets really big, meaning our wall gets really thick, the total resistance to heat transfer is going to go up. If our thermal conductivity gets really, really high, like we're switching from wood to metal, then and this is conductive thermal resistance, our conductive thermal resistance will go down drastically. Or if our wall gets bigger, we would naturally expect less thermal resistance by conduction. So and I do want to point out, this is not the total thermal resistance, this is the conductive thermal resistance. So in the next few lectures, we're going to figure out how do we add this conductive thermal resistance to the convective thermal resistances. And we'll bring this back to a rate law. These are rate problems where to get the total rate through multiple media of heat transfer, we would apply this thermal resistance method, which lets us lump these different modes of heat transfer into one single equation. There you go. Uh-huh.